The next section of the water efficiency category in LEED talks about innovative wastewater technologies. Next slide. The Stinky Killer being our toilets that account for 25% of daily water use in the United States. That's 1.6 billion gallons per year. It's pretty unbelievable that still half of the toilets in the US are inefficient and use at least 3.5 gallons per flush. New codes mandate 1.6 gallons per flush thanks to Energy Policy Act of 1992, but there are a lot of pre-existing toilets that still exist and need plumbing upgrades in order to reduce this problem. High efficiency toilets, known as HETs, only use 1.28 gallons per flush, which is about a 20% savings compared to the Energy Policy Act baseline of 1.6 gallons per flush. This has synergy with the water reduction requirements of Water Efficiency Prerequisite 1, which is a 20% reduction in overall water use. Keep in mind that does include sinks, showers, and other fixtures. An average home with 10,000 flushes per year, for example, can save 22,000 gallons per flush compared to the old 3.5 gallon toilets. You've seen these toilets, it feels like you're in an airplane. Or in a home that did have the 1.6 gallon toilets, you still can save about 3,200 gallons with high efficiency toilets. Now, in making your decision for plumbing upgrades and what to choose, making sure they're still functional, you really have to take into consideration things like vacuum pressure. When you're using less water, you still want to make sure the toilet is functioning as it needs to. And a great resource for that is the WaterSense resource online that the EPA came up with. There's also utility rebates, and take in consideration that you're going to save money on your utility bills as well. The LEED credit that addresses this is Water Efficiency Credit 2, Innovative Wastewater Technologies. This is a credit that was more heavily weighted in LEED 2009 version 3. 2 points are available. The intent is to reduce generation of wastewater and potable water demand while increasing local aquifer recharge. One example of this is composting toilets. Not as common, but you're seeing more variations of this. Once again, same with water efficient fixtures and high efficiency toilets. You just want to make sure that functionality stays in terms of no odor. This little diagram here shows that you need a fan and that you're actually discharging those fumes. Temperature is important, and if you have it indoors, you want to make sure that you have a complete system, and maintenance is going to be important. I know my grandma had an outhouse at our mountain house, and to keep the outhouse running properly, we would have to add lime to it. So there's some natural ways to deal with odor and help to decompose. Water Efficiency Credit 2, Innovative Wastewater Technologies, has 2 options to comply. Option 1 is to reduce potable water for sewage usage by 50% of your annual generation of black water. Black water being your wastewater. Water conserving fixtures include low flow fixtures, composting toilets, and waterless urinals. Waterless urinals are another option that require facility manager education on how to keep up on those. There are complaints about smell and other things not working as well, but that really has to do with maintenance issues and making sure that your facility staff understands how to maintain those type of water conserving fixtures. Non-potable water includes captured rainwater, recycled gray water, and on-site or municipally treated wastewater. So keep in mind that we're really trying to conserve on using potable water for things other than drinking. So alternative uses of water also help towards these credits in the water efficiency section. That's a common theme throughout these credits and will help you on questions about synergies on the test. How these fixtures work. For example, a wireless urinal might have a liquid cap that traps urine in a cartridge as it makes its way down the drain. That liquid on top is a sealant for any odors, and the urine is heavier and is able to go through that more buoyant sealant liquid. Wireless or composting toilets, you see a few variations here, from something that looks like a tiki hut outdoors to something that looks more like a conventional toilet. So the typical composting process includes a wireless microflush or urine diverting toilet. Oxygen demand is crucial. You can see good bacteria is key in this. So you want aerobic bacteria at work at all times. You need a curing zone and a finishing zone. And if these are all functioning well, you shouldn't have any odor problems as long as you're also exhausting at the same time with the fan. So in this example, there is a little bit of energy needed, but at least you're saving on water. But you always have to look at those trade-offs. Option 2 is to treat 50% of wastewater on site to tertiary standards. This could be packaged mechanical wastewater treatment or a more natural system such as a living machine that uses bacteria and aquatic vegetation, and lastly, fish and wildlife to treat black water. As mentioned, a potential trade-off could be optimizing energy performance since there's more energy for treating on site. Although you could do something more innovative like an anaerobic digester, then that uses the waste for then creating energy. Your calculations for this credit are based on the yearly amount of black water from flushing fixtures only. The water use reduction is the difference between the baseline case and the calculated design case. So it's very important in these credits with calculations to understand the difference between baseline and design case. Your baseline being the conventional systems per your code. Rates are based on fitting and fixture consumption rates, such as gallons per flush, and occupants' estimated water use. So you want to take into consideration the occupants in the building, how often they're in the building for your full-time equivalent occupants, and also male versus female ratios, since urinals are only applicable to males and women are seen to be making more flushes in toilets. So it's important to take that into consideration, the calculations. You need to know standards. For this credit, it's the Energy Policy Act of 1992. This is similar for most of your water efficiency credits. And remember, your design case, you need to use flow rates and flush volumes for installed plumbing fixtures and fittings, and then subtract any non-potable water use. Once again, this could be gray water reuse or rainwater harvesting. And for your baseline case, you can use what was calculated in Water Efficiency Prerequisite 1. For documentation, you'll need plumbing drawings with data on treatment facilities, your calculated occupants, being your FTE, baseline and design water usage for sewer conveyance, and total non-potable water supplied or annual quantity treated water. So this could be rainwater harvesting reuse, gray water reuse, or if you're treating your wastewater on site and reusing it for sewage conveyance. You want to make sure that if you're going to do something like rainwater harvesting or some of those alternative water reuse methods, that you discuss it in schematic design and integrate it throughout the process. Here in the picture you see a cistern buried underground, so that includes site planning and construction management coordination as well. Here's an example of various fixture types that save on wastewater. You have low flow water closets, composting toilets. In this case, you don't have any flow rate, so that's 0. Wireless urinals for males, obviously only applicable to that sex. And you combine all these together, multiply the flow rate with the occupants, and add those all together to get your total daily volume. Then you have your annual work days in order to get your annual volume. Then you want to subtract any rainwater or gray water reuse, since we're only talking about potable water savings. And that gives you your total annual volume. Here's an example of on-site biological treatment of wastewater. Here we have the toilet water going down to an anaerobic septic tank, then going to a closed aerobic reactor, and then open aerobic tanks, and then you have your clean effluent out. And this could be going into a constructed wetland, which also has synergies with open space and site remediation and habitat from the sustainable sites category of LEED. Once again, always thinking about synergies and how these credits interrelate with each other. This can also help with stormwater credits with sustainable sites if you have a constructed wetland. Multiple synergies with that technique. So looking at the process for this innovative wastewater technologies credit, in pre-design, you want collaboration with the owner, architect, and engineer. You need to study weather data of both annual and seasonal precipitation and set goals early on in the process. In schematic design, you want to include mechanical and civil engineers to consider things like constructed wetlands, rainwater harvesting, and how those things interrelate with each other. You need to establish a water budget, because remember, things like a green roof can reduce the amount of rainwater you can harvest for reuse in things like toilet flushing. So you need to set that water budget to know what is available and estimate volumes of end uses of potable water. Investigate sources of non-potable water. This could be gray water reuse, condensate water from your HVAC system, or water treated on site. And then estimate feasibility and costs of different strategies. And make sure to take into consideration savings on your utility bills for water reuse in those feasibility and cost studies. So really looking at that life cycle costs and all the different costs that plug in, not just first costs. In design development, the engineering team should develop and design water reuse systems. And in your construction documents, the architect should work with the owner and design team to pick out the fixtures and make sure they're meeting the owner preferences as well. Once again, function is critical. And looking at third-party websites such as the WaterSense website by the EPA can help you make these decisions and get feedback beyond just the vendors. Benefits. You're reducing potable water needed for sewage conveyance. Once again, those are the stinky killers, and water, as we saw in the beginning of this section, is going to be something that we see a huge problem with in the United States in the next 3 to 5 years. Savings in water and sewage bills. So you need to balance the costs of upfront costs and utility savings. And understand that facilities that generate the largest amounts of wastewater realize the most savings. There's definitely economies of scale with things like anaerobic digesters, living machines, and actually treating wastewater on site. Related credits, so here we're talking about synergies, which is a quarter of your test. Include stormwater design, so once again, constructed wetlands and rainwater reuse, help with stormwater management. Prerequisite 1, water use reduction, so things like high efficiency toilets, working towards that 20% overall water use reduction. Water efficient landscaping as well, once again, especially taking into consideration if you're reusing rainwater, how that can be used for landscaping as well. If it's used for toilet flushing, make sure to include your water budget if it's supposed to be used for landscaping and for toilet flushing, because you need to take into consideration how much rainwater is actually available and how much you can store on site during the dry period. So that's part of that water balance calculation. Water use reduction, similar to prerequisite 1. And then water efficiency credit for processed water if we're talking about schools. Once again, you can talk about reusing condensate water as well. Maybe you're reusing from dishwashers and other processed water as well and reusing it for toilet flushing. So lots of synergies and ways that the water efficiency credits interrelate with each other, and also sustainable sites credits. And remember, these different technologies also affect your energy efficiency, which is energy and atmosphere, optimizing energy credit 1, which we're going to get to in the next section. Biological wastewater treatment. This is a picture of a living machine. People may think they're just touring a greenhouse if they're done well. So the toilet water flows through a series of holding tanks with fish and wetlands with plants for biological purification. So once again, it's going through a series of bacteria stages before it gets to fish. So it's very important to know exactly what stages and how long the water needs to sit in each tank before moving on. So there's definitely a science to this, but they can be very functional, very pleasant accents to a lobby, in this case kind of a greenhouse type of situation. Here's an example of a synergy with the energy and atmosphere section of LEED. So you can actually create energy from waste. This is an example of biogas from an anaerobic digester. The anaerobic digester is converting electricity and heat from the wastewater by the Synergy biopower system, by PowerBase in this example. So getting energy out of waste. Waste does not need to just go down the drain in this case. Wastewater treatment is very important to consider, especially in climates with water shortages. We were definitely looking at this when I was working for Sienna Architects on a project in Dubai that was a LEED neighborhood development pilot. We're looking at large-scale district-scale reverse osmosis technologies for drinking water systems. And there's also point of entry ion exchange water softeners. And those two are the most universal water treatment technologies used for both residential and commercial locations. I think we're going to see more and more of this as we have more water shortages in this country as well. Dow Water also has process solutions. Here are 2 examples, just showing what's happening in a large scale, industrial scale. Next slide. So this process is using electrodeionization, which is a continuous and chemical-free process of removing ionized and ionizable species from the feed water using DC power, which is also what comes straight from most PV panels. So it's used to polish reverse osmosis and permeate and to replace conventional mixed bed ion exchange. So it's very high level of filtration.